Thank you. My name is Megan. I'm at the Center for Computational Astrophysics at the Flatiron Institute, which, despite its name, does a lot more than just large-scale computation. So specifically, I'm in the astronomical data group, and I'm going to be talking today about the data and what kinds of observations we can do to learn about the possible compositions of exoplanets, and what observations we have done and what the state of the data tells us right now about this topic. So I'm sure that a lot of us in this room wish that I were able to stand up here and talk about what we see rocky exoplanets looking like. But as we've heard a lot about already, and we'll continue to hear throughout this workshop, making direct measurements of exoplanets is really difficult. And even for the small number of planets where we can hope to get a direct image or a direct spectrum, it'll only answer questions about the outermost layers of the planet. We're never really going to get directly at the compositions of the cores and mantles of rocky exoplanets, and these things are key to planetary habitability. So how can we start to answer questions about the bulk compositions of planets? Well, it's hard to look inside of a planet, but one thing that we can do easily is look at stars. Thank you. I'm glad that I'm not too old to make good memes. So we have a lot of data out there for stars. And everything I'm going to be talking about today is basically, what do stars tell us about planets? So why would we look at stars? Why am I talking all about stellar compositions right now? There's a few different reasons for this. So the fundamental connection between stars and planets is that they form side by side from the same primordial materials. During the process of star formation, planets are also forming around the stars, as we've seen in really spectacular ways with recent ALMA images, for example. So that has a couple of implications here. One is that the materials that go into the star also go into the planets. And so whatever the star is made of, we can kind of regard that as a fossil record of what the protoplanetary disk was made of at the time of planet formation, and make inferences about what the raw primordial building blocks were available to make planets, and especially terrestrial planets, in this particular system, in this corner of the galaxy. There's another effect on top of this, too, that I want to point out, which is that at the time of planet formation, at the same time, material is going from the protoplanetary disk onto the star through accretion of the disk onto the outermost layers. And so in some cases, we can even hope to see almost a fingerprint of planet formation that's preserved on the stellar composition, because this material from the disk may have ended up on the outermost layers of the star. And so maybe this sort of planet-cleansed gas and dust coming from the disk is still being preserved on the star today. So there are a couple of different reasons why we might be able to use stellar compositions to tell us about planet characteristics and planet formation. And before I get too much into the results of what we're seeing, I want to spend a little more time talking about how we actually measure the compositions of stars, what the state of the art is, and what the caveats are to keep in mind here. And just for a little bit of background, so everyone's on the same page, this is the typical definition of an abundance. In this case, I'm showing you what we often call metallicity in astronomy. It's the relative abundance of iron and hydrogen. And so it's a logarithm of the number of atoms in a given unit volume in the stellar atmosphere relative to that same ratio for the sun. And so I think it's worth really emphasizing here that everything about stellar abundances is done differentially, or in a precise but not necessarily accurate way. We're always measuring abundances relative between a couple of different atoms, and we're always measuring them relative to generally the sun or some other sort of well-known star. And so that's going to be a theme that'll keep popping up. And so here's my attempt to put together a sort of cheat sheet of what sorts of abundances we can hope to get for stars. And for the most part here, I'm talking about visible and near-infrared surveys of FGK stars, generally main sequence, but also somewhat evolved stars. So the easiest thing to measure is iron. And then we kind of go down the list from things that you can measure fairly well and fairly reliably if you have a decent high resolution, high signal to noise spectrum, all the way down to things where you're going to have a really rough time measuring this. And I'm sorry to say that phosphorus is on the list of really hard. Hopefully in a few years down the line, the ordering of this list will have changed. But right now, this is kind of the state of what you can expect to get if you were to query an archive of stellar abundances. And it's worth pointing out that the ease of measuring something in a star is not necessarily related to how common that element is throughout the universe. There are things that we know are universally everywhere, like lithium and carbon, that are pretty hard to measure in stars. And it kind of works out to depend on the frequency of strong spectroscopic absorption lines in the regions of wavelength space that we can observe from the ground here on Earth. Also the sensitivity of these lines to various non-equilibrium chemistry things that may be happening in the atmospheres of the stars that we don't understand. And there are various complicating factors that make some very common elements still pretty challenging to measure. I will again plug the Hypatia catalog that popped up earlier today. Natalie Hinkle has really done a great public service to astronomy by putting together a list of many different stars that have precise measurements. And you can see from this big histogram of the different elements present in the catalog that there are certain elements that are almost always measured for stars, and there are other elements that are really difficult to find. But on top of that, I guess it's worth saying that just because they're there doesn't mean that the measurements are necessarily super precise. This histogram obviously doesn't take into account the confidence with which we know these various things. And so I do want to talk a little bit more about how the measurements get made in terms of what the biggest stumbling blocks are and how we know whether or not we can sort of trust measurements down to the precision that we want to look at planet scale differences between stars. So in general, when you're measuring the composition of a star, you're going to look at a high resolution spectrum. And this example is just showing a little tiny snippet of one of spectra of a couple of different sun-like stars. And I've labeled it with the elements that and the species that correspond to these different lines because it's important to note that we're not only able to get different elements out of these spectra, we're also able to get, in some cases, different ionization states, which is very important because measuring measuring ionization states of iron, for example, allows us to learn more about the stellar atmospheric parameters, the surface gravity on the star, which then feeds back into telling us how to interpret the absorption in the spectrum. So it's all a bit of a cyclic process where you take a spectrum, you measure the amount of absorption, you take a guess of what stellar atmospheric model you should use based on what you think the temperature, gravity, overall metallicity of the star is. You kind of tweak that with the iron lines that you've measured in the spectrum until everything looks good and you're confident that you have the right atmospheric model. And then you can finally believe the abundances that come out that were translated from amount of absorption in the spectrum to number of atoms through the means of atmospheric models. There's one issue with this, which is that stellar model atmospheres are not perfect. So there are a lot of simplifying assumptions that we have to make to get robust calculations of, say, the pressure temperature profile in the atmosphere of a star. And we know that stars themselves violate a lot of these fundamental assumptions of time invariance, homogeneity across the surface, lack of sort of evolution, lack of magnetic fields, you name it, there's probably complicating factors. And one way that this manifests is that as you go across a grid of different stellar models and look at stars that have different effective temperatures, you end up getting these systematic effects in large surveys where stars of different effective temperatures or different stellar types appear to have different abundances at quite a large level for basically all different elements that you can measure. And this is basically an imprint of imperfections in the stellar models. So what can we do about this? If we just sort of subtract out these trends, we're still not necessarily going to be able to trust the abundances that we've measured to below a 10% precision or something. And when we're talking about the sorts of scales of masses that go into a terrestrial planet, 10% is on the large side of what we would actually like to see. So one way that we can get around this, and something that I've worked on a lot, is twin star spectroscopy, where we select the sample of stars that we're looking at to occupy one narrow region of the model atmosphere grid. And if we've measured all of the stars with the same effective temperature, essentially, and we can use the same stellar model to translate from the spectral absorption feature to the abundance that we get out, essentially our stars might be wrong because the models are wrong, but they'll all be wrong in the same way because we've used the same bad model for them all. So that's a very simplified way of looking at it, but based on tests that we've done, this does seem to work quite well. And we can get down to about 2% level precision on the elements for which we're able to measure a lot of lines in the spectrum. So that's about 20, 25 different elements. All right, so that was a bit of background. Now I want to talk more about results and what we as a field have seen in terms of links between planets and the compositions of their stars. So the first thing to start with, I think, is the most classic result of this little subfield, which is the connection between stellar metallicity, and by metallicity, I basically mean iron abundance, although we use that as a proxy for all heavy elements, and planet occurrence rates. And this is one of the first real results of exoplanet demographic studies, that hot Jupiter planets tend to occur much more frequently around metal-rich stars. So this is classically interpreted as evidence for the core accretion model, where if you have a lot of metals in the disk surrounding the star, then you form a core very quickly, and then the core is still around while there's lots of gas present in the disk. So it has a fighting chance to accrete lots of gas and turn into a Jupiter rather than staying just a planetesimal core. You might be able to predict from that that these rocky planets that don't have large atmospheres won't be so sensitive to the timescales of planetary cores forming, and that seems to be correct. This is still a debated result that I'm sure will get even clearer with tests and others, but it seems right now like Earth-like planets don't really care about the metallicity of their host star. And to make things even more complicated, some recent work by John Brewer has shown that compact multi-planet systems, like the ones discovered by Kepler, tend to actually prefer low metallicity host stars. So there's some interesting results coming out of the look at stellar metallicity and planets. And a lot of these kind of connect to the idea of the star as a fossil record of primordial conditions under which planets are forming. But I do want to go a little bit beyond that and talk more about all of these other elements that we can measure and what those elements might tell us about once these planets are formed, what exactly in detail do they form out of. So there's been a fair amount of work done looking at certain key element ratios. Typically, carbon to oxygen and magnesium to silicon are regarded as the most important measurable planetary building block ratios. We think that if there is a lot of diversity in these ratios from star to star throughout the solar neighborhood or throughout the galaxy, that means that there will be a lot of variation in the geophysics of rocky planets that are formed around these stars. If you have a very different magnesium to silicon ratio from the Earth, say above 1 or even above 2, you're going to end up with more sort of magnesium-rich olivine type compounds, which has implications that I'm sure Cayman can explain much better than me if you're going to his hands-on session, but may have implications for things like plate tectonics on these planets. So it would be really interesting if we were able to label certain stars as being very magnesium-rich, or similarly label them as being very carbon-rich and therefore forming carbon-heavy compounds. But the results that we have found using this sort of differential twin star spectroscopy look show that for at least within the solar neighborhood, there actually seems to be very little variation. Most stars have carbon to oxygen and magnesium to silicon within about 10% of the solar value. And so at least within the solar neighborhood, it would seem like maybe the planetary building blocks that gave rise to the Earth are pretty much universal. That being said, it's very probable that in other parts of the galaxy, things like magnesium to silicon differ because of the different nucleosynthetic histories of other regions of the galaxy. And this is some recent work from Kirsten Blancato at Columbia showing that magnesium to silicon can vary quite a bit as a function of both the galactic radius of the star, the distance from the center of the galaxy, and its distance above the galactic midplane. And so there's still hope for very un-Earth-like weird worlds, but they might not be close enough for us to actually see much about them in the near future. I do also want to give one caveat, which is that you certainly can't take these results to mean that all Earth-like planets look like the Earth. We know that there's a ton of physics and chemistry going on within the protoplanetary disk, even fractionation within the planet itself while it's still young. And so I think it's still an open question whether or not star-to-star compositional variations in things like magnesium to silicon are actually a dominant source of diversity in planet compositions. There are plenty of other ways to get very different sorts of Earth-like planets. And finally, I want to touch a little bit on this question of whether we can actually see sort of secondary effects where the disk that got accreted onto the star at late time stages imparts some sort of signature of terrestrial planet formation. I think this is it's an interesting question that's definitely worth investigating, although I'm going to be giving this story with a lot of sort of cautions to it. So this idea really first became popular through Jorge Melendez's work in 2009, where he looked at about a dozen solar twin stars. He again used this differential twin star spectroscopy technique, and he measured about 20 different elements in these stars and found that when you take the average sun-like star and you compare it to the sun, the average sun-like star actually has more refractory elements, elements with high condensation temperature or rock-forming elements, than the sun does relative to the volatile elements. And the sort of trend that you see here in condensation temperature is a bit complicated to understand, but it essentially follows the predictions of taking a mix of about 4 masses worth of equal parts Earth composition and chondritic meteorite composition, and taking those out of the sun's composition. That's basically what we see today for the sun. So it's really hard to interpret this. It could equally likely mean that the sun is missing 4 Earth masses worth as planet-forming material, maybe implying that the sun formed more planets or more rocky planets than the average star does. It could also mean that other stars are enriched in 4 planet masses, 4 Earth masses worth of planetary materials, maybe meaning that sort of late-stage accretion events and destabilization of planetary systems are more common in other systems than they were for the sun. And on top of this, it might be a coincidence. It might not be planets at all. It might be some sort of ISM physics that we don't fully understand right now. But I think that this is it's an interesting look. And so to follow up on Jorge's work, I looked at a larger sample of solar twin stars, going from about a dozen up to 80 stars and expanding the elements that we looked at up to 30 different species, and found that these results do seem to bear out. It's probably not a statistical anomaly that we saw this earlier. The sun does lie at kind of the 2 sigma end of this general distribution of different amounts of refractory materials in stars. And again, it's really hard to interpret this, especially because we don't actually know what sorts of planets are around other sun-like stars, as Courtney was talking about. So we would love to be able to measure Earth-like planets or not around the other stars in this histogram and see where they fall and if there actually is a link to planets. One other thing that we can do is use sort of a more controlled laboratory than looking at the sun and a bunch of sun-like stars. We can look at stars that are in binary systems. And so Johanna Teskey and Semyoung Oh and others have done in-depth work looking at twin stars that are in binaries, where the 2 members of the binary have different planetary systems. And in some cases, they also have different abundance patterns that potentially show that planet formation did have a secondary impact on these systems. This is interesting because the binary system should primordially have exactly the same composition. So I think that this is something that's worth keeping an eye on in the future. We can also do this for star clusters, which similarly should have the same primordial abundances. So I think this is a promising road to go down in terms of looking for rocky planet materials in other stars and potentially being able to infer things about the occurrence or the characteristics of rocky planets throughout the galaxy. But we're a really long way from actually being able to believe these results. So I would just say, keep an eye on this stuff for the future. We would like to get better data. We would like to have better ways of modeling this. And we would like to have sort of more of these binary systems and others that allow us to interpret this in a more straightforward way. So I want to conclude by talking a little bit about the future of the data to answer these various questions about stellar compositions, planet compositions, and the links between the 2 of them. And I think the future is especially exciting for this, in large part thanks to Gaia, which is has already measured astrometry for 1 billion stars in the Milky Way. And we'll soon be coming out with even better astrometry and also measurements of planets on long period orbits. Probably tens of thousands of new planets will be found by Gaia. And Gaia has been getting a lot of excitement in the stellar spectroscopy community because it can allow us to kind of assemble the Milky Way in this dynamical picture. And a lot of people would really like to add a chemical component to this picture too. So there are quite a lot of dedicated surveys that are looking at the very same bright stars that are being observed in large numbers by Gaia and trying to get precise chemical abundances of many different elements for these stars. So thanks to this sort of neighboring community to exoplanets, we're really getting a lot more data that will be useful in the near future. And it's worth pointing out that all of the stars that Gaia and these ground-based surveys are looking at are also the stars being targeted by missions like TESS that are also looking at bright solar neighborhood stars, radial velocities, which have always and will always measure these solar neighborhood stars, and again, Gaia exoplanets. So we're getting a lot closer in the future to having robust abundance measurements for stars where we know a lot about the planetary systems on a lot of different orbital period and mass scales. So while a lot of the things that I was talking about were kind of with caveats about these are what the data say, but we don't know how far we can trust these things to tell us fundamental physical connections to planet formation, I think we're getting a lot closer in the near future to being able to actually make these inferences and test our hypotheses in terms of the connections between stars and planets. So yeah, these large populations are coming very soon. And with that, I will leave up some final points and take questions. Thank you.
Well, I just wanted to mention that NASA's SphereX mid-X mission, which will get spectrophotometry of tens or hundreds of millions of stars between 0.75 and 5 microns, is likely to provide additional data for improving the stellar models, the stellar radii, consequently exoplanet radii, and I'm not sure to what extent the composition plays into that, because I'm not quite sure how dependent the gross stellar properties are on the composition, but it could provide additional constraints on composition as well.
Yeah, that's very promising. Thanks. And I think also expanding more into the near infrared will help mitigate some of the problems with elements that we're only able to measure in very limited numbers right now.
I was wondering about the features of planets of Earth. So if you're saying that Congo will be able to release those features, is what I understand by that?
Sorry, I didn't quite hear that. Chondrals.
So from the previous slide you have about these features of planet formation on the environment and the stars, so that would be something like Congo meteorites, right?
Mm-hmm.
Okay.
Yes. Yeah, so.
Which I understand is a fairly old idea about chondroids. So it's just been essentially repeated for exoplanets. Essentially, the idea is passed on.
Right. Yes, so this sort of condensation temperature idea depends a lot on assuming that Earth-like materials and also chondritic meteorite-like materials are sort of universally formed things, which may or may not be true.
So I was curious about that histogram that you had of the basically the solar twins, right?
Mm-hmm.
I'm wondering if basically is there any information you can get for the age of a star from just a single spectrum? I know the age is one of those things that we really don't know, but I'm wondering if it's something to do with age or formation location in the galaxy, something like that.
Yeah, that is a really excellent point. So surprisingly, we can actually get quite a lot of age information for these stars, even though they're main sequence sun-like stars, which are typically really hard to measure. We have such precise surface gravities and temperatures for the stars that we actually can place them pretty well on isochrones. And so the closest thing I have to a plot of that is these left panels of the magnesium to silicon and carbon to oxygen. You can see that these are the same solar twins in the histogram. And they do span pretty much the full main sequence. And we can even see that there are some differences between stars that are the oldest, possibly thick disk population. That being said, we looked for connections between the stellar age and the stellar dynamics once Gaia DR2 came out and these condensation temperature trends, and didn't see anything obvious. And that's actually what the two different colors of the histogram are showing. GCE is galactic chemical evolution, and it's essentially saying before and after we account for the average abundances at different ages, what do we see in the residuals to that? And it seems pretty invariant or even orthogonal to that effect. But that's a really good point.
Okay, I just want to ask a question about spectral type, because many of the targets for terrestrial planets will be around M dwarf. So what's our plan to study elemental abundance around for M dwarf stars?
Yeah, that is a good question. I'm not the expert to ask on this, but my understanding is that we're getting closer to being able to measure precise abundances for M dwarfs, but it's never going to be quite as easy as FGK stars because we'll always have to go to a sort of synthesis technique rather than being able to isolate individual lines and individual species. So you're always, I think, going to have more sort of systematic uncertainties involved where you could be getting all of the elements wrong in similar ways and not be able to fully diagnose that. But again, I'm not a huge expert on this. Yeah, so aluminum is one of the elements that we can measure pretty easily. It is not too closely tied to magnesium and silicon actually, because it's not so strongly produced by the alpha process, and so like there's some nucleosynthetic effects that happen in there. I can show you some results later, but we generally see that like a lot of these other heavy elements, most of the solar twin stars at least have fairly similar aluminum to iron ratios to the sun.
These are all elemental.
Yes. Oh, that's a good point. Yeah, we have no idea about aluminum 26 in particular relative to other isotopes.